welcome to our course Metallocene and Metal-carbene based organometallic compounds for alkene polymerization. So, we now have started the metal-carbene complexes for using the catalysts for very efficient polymerizations reactions, alkene polymerization reactions. So far, we have studied and in a very quite depth about the metal-carbene complexes and their electronic structure, their chemical structure, their the synthesis and the type of the ligands, and also ancillary and what are the ancillary ligands and how it influences its reactivities, geometries, and obviously the electronic properties. We also discussed the types of metal alkene complexes, as example Fischer-carbene, Stock-carbene, what are the basic difference in structure and the geometry and the metal centers as well as the ligands. And also we have discussed about the various type of alkene metathesis reactions. Today we will concentrate about its versatility and the and its mechanism of the alkene metathesis reactions. So, the concepts we will cover today is the versatility in the alkene metathesis reactions and the very well accepted and the mechanism for this kind of alkene metathesis reactions. Okay. So, with this the key points of our today's lecture will be obviously the reactivities mechanism. We will more concentrate on the mechanism and the versatility in the alkene metathesis reactions. Okay. So, this one now we all know that what is alkene metathesis reactions. So, this is one example of the metathesis reactions where you will see that this is a alkene. Okay. So, here in one alkene, and here you will see by using the metal-carbene catalyst you are actually making the two new alkenes. Okay. So, here from you will see that it looks like that somebody has broken this part and then again it is threaded. So, like this red part you will see is this one, and another half of this red part. If you thread it, you will get this alkene, and the blue part. Okay, similarly, if you thread the two blue parts, you will get this alkene. Okay, so this kind of reaction is called a metathesis reaction, and we are now well aware that what is metathesis reaction and what are the catalysts. Now, today we will discuss that what are the versatility in this kind of metathesis reactions. As if you recall, I told in the last classes that this is a single key for multiple locks. That means a single catalyst can do a various type of metathesis reactions. So, that we will today discuss. Okay, and this is just to recall, because we all have discussed in very depth about it, about this, its geometries, the electronic properties, and also the synthesis. So, just to recall that this is actually the first Grubbs catalyst that is called the first generation. Sometimes it is called just simple G1. Okay, this is the Grubbs second generation catalyst. This sometimes called just simple G2, and here you will see that this is actually the N-heterocyclic carbene, NHC. Okay, and this is the Grubbs third generation catalysts. Okay, here this is also NHC. Okay, but here you will see that one cyclohexyl phosphine has been substituted by 3-bromopyridine, and this one, the Hoveda-Grubbs catalysts, sometimes we call just a GH catalyst. Okay, and there are a different type of others like a Blechert and others kind of metal-carbene complexes, and here you will see all are ruthenium based plus 2 oxidation state, and you will see the reactivity is generally increases from left to right, and these were needed because all the substrates are not equally reactive. That we'll discuss, okay, in the following classes. Okay, and you know that these kind of catalysts are very famous for different type of alkene metathesis reaction that actually we are going to study today, and that's why it's so popular. This is another very interesting point, is that this kind of catalysts are also tolerable to compatible to different functional groups. Okay, so metathesis reactions, actually the mechanism is initially it was proposed, it was seen to be very complicated, and that's why different groups proposed different mechanism, and among them two mechanism, that is the pairwise and non-pairwise mechanism, was reported, and it was proposed that it may happen through the two main ways, that is the pairwise and non-pairwise. In the last class, I very briefly mentioned in one class that what is the pairwise and non-pairwise. Today we'll discuss in more depth that what is the pairwise and non-pairwise. Okay, so this is, let's see, first discuss the pairwise. So pairwise is what? So like this is my metal centers, and if I have alkene, let's say this RCH double bond CH2, okay, so this can coordinate in pairwise, that is the one alkene pair, okay, one alkene pair is coordinated to the metal at the same time, and it forms a this kind of a transition state, okay, that is the four membered, but metal is coordinated with two alkenes. And what happens, you will see here that we will be getting the alkenes, okay, that is here this the alkenes CH2CH2. So this is the ethylene. So this is my ethylene moiety, and this is my R, okay, and this is H and H. Okay, so here you will see that in this pathway that from one alkene we are getting two alkene, that is this one and this one. Okay, okay. So trans to some extent trans isomers can also be formed, and the path B, that is also pairwise mechanism and very similar. So here you will see that this one can form the metallocyclopentane, and through this one then it forms a metal-carbene complex. So both the cases are actually, it is a pairwise because the two alkene, okay, are coordinated to the metal centers and form an intermediate. However, the modern however, the recent spectroscopic methods have proved that both the mechanisms are ruled out. That means the pairwise mechanism actually does not work. Okay, I will give one example that how it can be proved. So what is the more well accepted mechanism? That is this one, that is called the non-pairwise mechanism. Okay, what is the non-pairwise mechanism? So here you see this is my metal-carbene. Okay, okay, this is we have just taken as a general form, nothing, no specific metal-carbene. So this is assumed as a metal-carbene, and it forms a metallocyclobutane. So this is basically the reactions is we already discussed in the previous classes like that. So it forms a metallocyclobutane. This is called the metallocyclobutane. This is a intermediate, okay, and so and then the bond breaks just the reverse as it was formed. Okay, so how does it work? So it is basically what happens, the bond formation was in this direction. Okay, so now it will be just opposite in direction like the bond breaking will be just opposite direction, and you will get that this new metal-carbene, and this is your new alkene. Okay, and similarly cis isomers can also be formed. So again this new metal carbene, again that this is the new metal carbene that actually can again react with the another alkene and form the another new alkene, that is the ethylene in this case. Okay, so this is the ethylene. So this mechanism, that is the non-pair mechanism, is the most well accepted mechanism, and it is believed that metal alkene metathesis reactions proceeds through the non-pair wise mechanism, that is through a metallocyclobutane intermediate. Okay, I hope it is clear. Okay, so again these mechanisms are ruled out, that is the pairwise mechanism, and so no need to think about it. That is the non-pairwise mechanism, that is through the metallocyclobutane, is the well accepted mechanism for the alkene metathesis reactions. Okay, anyway, but what is the proof? Okay, this can be proved in by very easy experimental methods, by designing a suitable experiments. This is one of them, is a very well and famous experiment to prove that this proceeds through a cyclobutane, metallocyclobutane, that is the non-pairwise mechanism. So here what you have seen here, you will see that this is a cyclooctene, okay, and this is the 2-butene, okay, and this is 4-octene. So this is cyclic and this is acyclic, okay, with the same number of carbon atoms, C8 cyclic alkene and C8 acyclic alkenes. Now if you do the metathesis reaction, let's assume that you take a ruthenium to any Grubbs catalyst, okay, then what happened if you consider the pairwise mechanism, okay, then and cyclooctene should undergo the reaction, okay, and what you will get only the 12 member C12 and C16 at the initial step of the reactions. Okay, so in absence of metathesis between acyclic alkene and assuming pairwise mechanism, then at the initial stage you should get only C12 and C16, because if you recall this mechanism, this one, so this is, you will see that at the initial this is alkene will form, so C12 and C12, that is the two alkene you can get it. But what we observe experimentally, we observe the C14 and C6 also. And how it is possible? If you consider the non-pair wise, then only this C14 and C6 can be formed. Okay, so because see, from C8 you will get C6, because you will get from C8 you will get C6 plus C2. Okay, so this observation is consistent with the non-pair wise mechanism. Okay, So the observation, the statistical distribution of different alkenes at the initial phase of the reaction is consistent with non-pairwise mechanism, that is through metallocyclobutane. Okay. So another very famous proof of whether it is pairwise or non-pairwise, that is this one. So here you will see that two alkenes has been taken, one is with deuterated and one with H2, CH2, CH2. Okay. Now, if all, here you will see that if in reality, in experiment, what you will get, you will see that all the isotopomers, that is this one, this one, this one, and obviously this one. Okay. If it is pairwise mechanism, then you should not have got this part. But as it is a pairwise mechanism, we get the statistical distribution as 1, 2, 1. Okay. So this actually clearly proves that the alkene metathesis reactions proceeds through the non-pairwise mechanism, that is through metallocyclobutane. Okay. So I think it is very clear. So again, you will see that if it is pairwise, then this one or this one will coordinate, this one or this one will coordinate to the metal centers, and you will get either CH2 ethylene, the non-deuterated, or the deuterated CD2 fully deuterated ethylene. If it is non-pairwise, then only we can get the partially deuterated ethylene, that is the CH2 CD2, that is 1:2:1 statistical distribution. Okay. So as experimentally all the ethylenes, okay, all the ethylenes were observed. Okay. And so it directly proves that the mechanism proceeds through the non-pairwise mechanism. Okay. So now with the knowledge of this experiment, okay, and the concept, okay, the following mechanism can be constructed. You know that this is called the catalytic cycles. We in organometallic chemistry or catalysis, we try to construct the catalytic cycle to show that catalyst can be again back to the initial state, so that it can be reused. Okay. So here you will see that if we start with, let's say this is my the pre-catalyst or the metal-carbene catalyst, okay, catalyst, and you will have to have some make the coordinately unsaturated, so that the alkene, that is the new alkene coordinates. So this is called the initiation step, so that the 1L comes out, okay, and you get the back end site, okay, and then you will see that this alkene coordinates, and it forms a metallocyclobutane, okay, and then you get your this intermediate, okay, and then again this metallocyclobutane breaks, okay, and this way. So you will form a new metal-carbene, okay, and this new alkene also will be formed, and then you will see again the alkene will coordinate and form the again the metallocyclobutane, okay, and again it will break, okay, like that, and this breaking will be just the reverse of the bond making. So bond breaking and bond making, it will be just the reverse direction. Okay, so that's why you will see that this alkene metathesis, the catalytic cycle, is basically the sequence of 2+2 cycloaddition and cyclo reversion. You will see that this addition and this is the cyclo reversion, breaking and forming the cyclobutane and then making the cyclobutane, and it is a repetitive pathway, okay, through the metallocyclobutane intermediate. Okay, so I hope this is very clear. So alkene metathesis mechanism proceed through a 2+2 cycloaddition reactions through a non pairwise mechanism through metallocyclobutane formation. Okay, now mechanism is understood. Okay, how the reaction proceeds. Now I will discuss about the versatility in alkene metathesis reaction, and after that I will come to the alkene polymerization reactions, how it is possible by the this kind of catalyst. Before that, it is very important to understand that how the other alkene metathesis reactions are possible. Okay, then we will discuss that how it can be applied to polymerization and or polymer synthesis reaction. Okay, so first we will see that ring closing olefin metathesis. In the beginning of our metal-carbene complexes, I mentioned that different type of alkene metathesis reactions are possible, like ring closing metathesis, ring opening metathesis, cross metathesis, and very related to the ring opening is ring opening polymerization, ROM. Okay, ring opening metathesis polymerization. So this is the ring closing olefin metathesis reaction. So here you will see that this alkene is basically threaded, okay, by using the catalyst. Okay, so this kind of reaction is called the ring closing metathesis. That means you are suppose I have alkene this here, and what we are doing, we are basically closing the ring and forming the another this alkene. Okay, if it is CH2CH2, okay, and the N. Okay, so here you will see that this is called the ring closing metathesis reactions. Okay, so obviously from this reaction you will see the different type of value-added organic compounds may be synthesized. As example, if X is heterocyclic, then different type of heterocycles may be synthesized, and these are very popular in organic chemistry, okay, to make different functionalized organic compounds, and very quite popular in also in the medicinal industries. So here you will see that different type of examples, like here you here see here that how different interesting functional the cyclic rings can be formed by the different type of catalysts, or like Graf's catalyst or different modified the metal alkene catalyst. So here example, here you will see it's basically here we are threaded, okay, this alkene, okay, and here you will see it's just threaded this one, okay, and you getting from a acyclic to a cyclic organic compounds. So not only that, these ring closing metathesis reactions are very popular and widely used in multiple steps in synthesis of natural products. Like one example is the benzylamine A. Here you will see this step, you will see that this is actually the ring closing, okay, metathesis reaction. Okay. So this is ring closing metathesis reaction called, or sometimes called RCM, ring closing metathesis reaction. So here you will see that this step is this is just a one example. There are numerous examples where where different for synthesis of different type of natural products in one or more than one steps, the Grubbs catalysts have been used, okay, very widely, Grubbs or Stock type of metal-carbene catalysts. So you will see this very popular nowadays, and here you will see the very similar, the different type of heterocyclic organic heterocycles can also be synthesized. You will see that depending of your N, okay, so you can make 5-membered, 6-membered, 7-membered heterocyclic compounds, different functionalized, okay, functional heterocycles, and is a very effective method, and that's why it's so popular in organic synthesis and also in medicinal chemistry. So all the Grubbs catalysts, okay, Grubbs catalysts G1, G2 are very effective, okay, for this kind of a reactions. So not only the just a ring closing metathesis, the cross metathesis reaction is also very popular in organic chemistry and also different industrial domains to make the new alkenes or modified alkenes. Okay, so these are lots of synthetic values and also lots of opportunities to make new alkenes. Okay, and here you will see this is just a guidelines I have shown here, that how we'll choose or how we'll justify that what alkene will be more reactive, which one will be not reactive or less reactive. You can categorize by the different type, like type 1, type 2, type 3, type 4. The type 1 are generally the unhindered and electron rich. So these are the type 1, and more hindered, that is the less electron rich, these belongs to the type 2 and 4. Okay, and why these are important? These are important to judge that which alkene will be more reactive for alkene metathesis reaction. As example, for type 1, it undergoes the rapid homodimerization, okay, and these homodimers are conjugal, that means it can react again. Type 2, slow homodimerization, type 3, no homodimerization, and type 4, olefin inerts to see cross metathesis reaction but do not deactivate catalysts. Okay, so it just acts as a ligand. Okay, so reaction between two olefins, so this is the guideline. So if you react with two olefins, you will get a statistical cross metathesis reactions. Reaction between two olefin of same type, okay, you will get the non-selective cross metathesis reactions, and reaction between olefin of two different type then you will get the selective cross metathesis reaction. Okay, that means if there is a enough difference between the alkene metathesis, the reactivity of the two alkenes, then I will tell that yes, I will get this product in a major amount. So this is good to know, very useful guidelines to choose the or to judge that what product I will get, or what ligands or what alkenes I will take it. So this is a very useful general guidelines. Okay, this is just for the extra knowledge. I have tabulated this one, so this is basically nothing but continuation of this one. Okay, so here you will see the different type or some examples of the cross metathesis reactions, and here you will see that Stock molybdenum catalysts or Grubbs 2 catalyst can undergo very efficient cross metathesis reactions. And here you will see, as I told, that these kind of catalysts are very compatible with different functional moieties. Okay, here you see ester, alcohol, even the borate, okay, even the amines. So that's why it's so useful to make the functionalized new alkenes. Okay, so here you see functional, okay, alkenes. Okay, so these are, and then after that you can again modify the alkenes, okay, to different acids, alcohols, esters, whatever you need. Okay, if you, so this is really very useful method and very effective method, okay, for to make a new value-added alkenes. Not only that one, you can also make a stereoselective, make this reaction stereoselective by choosing the chiral, okay, chiral catalyst. Okay, we have already discussed about how you can make a particular reaction is asymmetric, okay, by choosing the chiral catalyst which proceeds through the CSC, that is the catalyst site control mechanism. Okay, so here you will see that if you use the chiral catalyst, you can control the stereoselectivity and you can get a particular stereoisomer and here you will see one example. So what you will see that you are basically you are closing, okay, here you will see that you are making this reaction stereoselective by the chiral modified, okay, modified Stokes catalyst. Here you will see that the chirality is coming from the this axial chirality of substituted biphenyl. Okay, so that you know, okay, that how this axial chirality plays a role to make optically active. Okay, okay. So here these are some basically this is just for your knowledge and showing the examples to prove that how versatile these reactions are. Not only that, that's not only this, that there are various examples here. You will see again that you are how you can make the ring opening, okay, metathesis reactions by ring opening and ring closing both here actually. So here basically what you are doing, you are closing the metathesis closing the ring here and here the opening, okay, so simultaneously ring closing and ring opening, okay, reaction, and here you will see that how you can make the stereoselective. Okay, so here also same thing. So using the chiral metal-carbene catalyst. So these are some kind of a example that how you can design your catalyst to make the chiral and to make the reaction stereoselective. Okay, so these are again another examples. Okay, so you will see that here not only the Stokes, there are different catalysts like ruthenium catalyst. Okay, the Graf modified Graf's catalyst also you can make the chiral, and you will see that like for molybdenum, if you this is like a binap. So again it is the axial chirality. Okay, and this is the chiral ruthenium Graf's type of catalyst. This also chiral catalyst, and this chiral catalyst actually control the stereoselectivity of different type of metathesis reactions. So in conclusion, you will see that versatile alkene metathesis reaction by metal-carbene catalyst complexes. Okay, you will see that ring closing metathesis or ring opening metathesis or the cross metathesis, okay, provides very effective route to synthesize new alkenes, okay, and mechanism we have learned that proceeds through metallocyclobutane. That means you will see that it's proceeds through a sequence of cyclobutane, metallocyclobutane formation, and then metallocyclobutane breaking. So and this through actually the non-pair wise mechanism. That means at a time only one alkene is coordinates and forms the metallocyclobutane. Okay. So the today's lecture, you can read the books, mainly the Hartwig and the Crafty's book. Okay, most of the contents are available in these two books. Okay, so thank you very much for today's lecture, and in the next class we will discuss about the another versatile, that is the main topic of our metal-carbene classes, that is the polymerization, alkene polymerization by metal-carbene catalyst. We will discuss how this polymerization proceeds, and again the versatility of the monomers, and what are the scope of and the future prospect of the alkene polymerization by metal-carbene catalysts. Okay, thank you and see you in the next class.